Topic 3, finite control volume analysis. Apply the conservation of mass equation to balance the incoming and outgoing flow rates in a flow system. So a control volume is a finite or infinitesimal region in space that represent our system. For our case, we are going to focus on the Eulerian type. It means we are going to fix a control volume. Energy is conserved property. It cannot be created or destroyed during the process. M dot equals to rho VA and V dot is AV or VA. So M dot is rho V dot. Unit, volume flow rate, meter cube per second, mass flow rate, kilogram per second. Let's see the conservation of mass. The conservation of mass principle for a control volume. So now we are talking about control volume, the volume that encloses our system. The net mass transfer to or from a control volume during a time interval delta t is equal to the net change, increase or decrease in the total mass within the control volume during delta t. Suppose we have a bathtub here and then we open the water tap. Just imagine for a certain times we put 50 kilograms of water inside the bathtub. And then at the same time, we release 30 kilograms from the drain. The amount of water that we add to the bathtub is 50 minus 30, 20. Another example, suppose that we have a classroom. The classroom has two doors. One is in front, one is behind. If 10 students coming from front and then 3 students going out from behind, we can say that the increase of students in the class will be 10 minus 3, 7. We have the conservation in this case. For example, in this case, 30 plus 20 is 50. In the case of the classroom, we have 3 plus 7 inside equal to 10 coming inside. So that's what we call conservation. The sum will be constant. For the conservation of mass, the increase of mass in the control volume is equal to the mass coming in minus mass going out for a certain period of time, delta t. Or this one, mass in minus mass out equal to delta mass in the control volume. And this one is observed for a limited period of time for delta t. As a matter of fact, this one is all divided by delta t. When delta t becomes very small, instantaneous, m in minus m out over delta t becoming this one. It becomes dm over dt for a control volume. And then m in over delta t becoming m dot. M out over delta t becoming m dot out. So we have m dot in minus m dot out equal to dm over dt for a control volume. Mass balance is applicable to any control volume undergoing any kind of process. That is the conservation of mass. The conservation of mass is also named continuity equation. This is the equation that you have seen. M dot in minus M dot out equal to dm CV over dt. CV here is control volume. Okay. In more general term, shape, the conservation of mass is written like this. So this is the integral equation. This part is depending on t, which is this one. This one is m dot out minus m dot in. So this is the general equation for conservation of mass, or it is something like that. Now, when we have steady flow, steady means it is independent of time. It means it doesn't change with time. For example, if you drive a car with 110 km per hour, you maintain that 110 km per hour. It means you are steady. There is no acceleration. So steady means it doesn't change with time. So if it doesn't change with time, it means it is constant according to time. When it doesn't change with time, it means the term with respect to time is constant. When it is constant, when you derive with respect to time, it becomes 0. So this part will be 0. Or this part will be 0 because you differentiate with respect to time. So d over dt will become 0. So for steady flow, m dot in minus m dot out equals 0. or m dot in equal to m dot out. In the case of the classroom, if 5 students coming in, 5 must go out, because we don't accept any more increased number of students in the class, for example. So if we have 2 inlet, 1 outlet, our control volume is inside here. So if from 1 inlet we have 2 kilogram per second, for another inlet is 3 kilogram per second, then at the outlet here, we need to have 5 kilogram per second. That is the steady flow. We can write sigma m dot for inlet equal to sigma of the m dot in outlet. If we have single stream, it means only 1 in, 1 out, m dot 1 equal to m dot 2. M dot is equal to rho AV. So rho AV1 equal to rho AV2, rho VA1 equal to rho VA2. So this equation, again, all this one is valid only if we have steady. If not steady, it will be this one. If steady, we have this. For multi-inlet, multi-outlet. For single inlet, single outlet, we have this. Or this one. Now, if we have on top of the steady flow, incompressible flow. Incompressible means rho constant. Rho doesn't change. So if suppose that we have a rho coming here, rho 1, rho going out here, the rho must be constant. That is incompressible. Incompressible means rho constant, or rho 1 equal to rho 2. If rho 1 equal to rho 2, it means I can cancel that one. So I have V1A1 equal to V2A2. V1A1 is V dot. This is volume flow rate. V dot 2. So in the case of incompressible plus steady, we are going to reduce the delta m dot equation to delta v dot equation. If we have multi-inlet and multi-outlet, but if we have only 1 inlet, 1 outlet, we have this one, v dot 1 equal to v dot 2, where v dot is v1a1, v dot 2, v2a2. V dot constant is correct if we have steady plus incompressible. There is no such thing as conservation of volume. We can say conservation of mass. We never say conservation of volume. It doesn't exist. But for steady flow and incompressible, we have V dot constant, but we never say conservation of volume. In normal operation, liquid is always assumed to be incompressible. Water is incompressible under normal operation. So for water, we can say that V dot constant or V dot 1 equal to V dot 2. But for air, be careful. Air is compressible. So you cannot say V dot 1 equal to V dot 2. Usually for air, we say m dot 1 equal to m dot 2 or m dot 1 constant. However, if the speed of air is very slow, if the Mach number less than 0.3, then flow is incompressible. But for Mach number bigger than 0.3, the air is compressible. For water, it is incompressible. For example, for this, a compressor is to compress air. Even from the name, we know that it is compressible. In this example, we see that m dot 1, 2 kilogram, m dot out, 2 kilogram, for sure, if we have steady flow inside. But volume flow rate, V dot 1 is 1.4 meter cube per second. Volume flow rate at the exit is not the same, 0.8. A garden hose attached with a nozzle is used to fill a 10-gallon bucket. The inner diameter of the hose is 2 centimeters, and it reduces to 0.8 centimeter at the nozzle exit. If it takes 50 seconds to fill the bucket, with water, determine the volume and mass flow rate of water through the hose. B, the average velocity of water at the nozzle exit. For this case, we are going to put assumptions. Water is nearly incompressible substance. Flow through the hose is steady. There is no waste of water by splashing it. For the property, we take the density of water 1000 kilogram per meter cube or equivalent to 1 kilogram per liter. So now for the first question, this is the system. The pipe, the nozzle. So we have the pipe is 2 centimeters. And then we have the nozzle here, 0.8 cm. And then we put the bucket. So this one is 10 gallon. Now to fill this 10 gallon, you need to do it in 50 seconds. So from here, you can obtain what is the V dot. We know that the 10 gallon will be filled up in 50 seconds. So what is the volume flow rate? Is 10 gallon divided by 50. What is 10 gallon in liters? Divided by 50. So 0.757 liter per second. Now, mass flow rate, you just multiply the volume flow rate with rho, 1 kilogram per liter. If you have meter cube here, you multiply with 1000. So you have 0.757 kilogram per second. Now the second question. What is the average velocity of water at the nozzle exit? If this is V1 and here is V2, to find the answer, you need to calculate the area of the nozzle. We have the diameter 0.8, so the radius is 0.4 centimeter. So you need to convert this one to meter. You divide with 100. So you have this meter square. And then we have the previous one, 0.757 liter per second. That is equal to VE times AE. So it means VE equal to V dot over AE. V dot is this one. AE is the one that you calculate. 1 liter is 1 over 1000 meter cube. So you have 15.1 meter per second. What is the velocity in the pipe? It is 2.4 meter per second. So we know what is a control volume. We have seen conservation of mass. What is mass flow rate, volume flow rate, conservation of mass principle, mass balance, what is steady flow. In the case of incompressible, we have seen all this one.